Good afternoon to all. Okay, principle of operation of DC generator. So, am I audible? Am I audible? Am I audible? Okay, so let us see the principle of operation of DC generator. So, the DC generator operates on the principle of Faraday's law of electromagnetic induction. It operates on the principle of Faraday's law of electromagnetic induction. So, I'm taking the pen. It operates on the principle of Faraday's law of electromagnetic induction. So, if magnetic field is varied with respect to the conductor, you can see conductor here. If magnetic field is varied with respect to the conductor, or if the conductor is varied, varied means if it is moving, if the magnet is moving or the conductor is moving, you can see here in the second diagram, conductor is moving, in the first diagram magnet is moving. So either the magnet or the conductor, any of these two is moving, EMF will be induced across the conductor terminals. So if the conductor terminals are having a closed path, then current will flow through the conductor. Okay, current will flow through the conductor if it is forming a closed loop. If the conductor is forming a closed loop, current will flow through the conductor. If I am not audible, please inform. So, when magnet is there, if there is magnet, there will be number of flux lines. So we can call them as magnetic lines of force. So the number of flux lines linking with the conductor, or there can be more than one conductor. So this I am showing here only one conductor. There can be more number of conductors. So they can form a coil. Okay, so they can form a coil. This is a coil. Okay, so they can form a coil. Okay, So the flux, magnetic flux linking with the conductor, if it is changing, then voltage is induced across the terminals of the conductor. So that induced voltage, you can denote it by E or V. You can even call it as electromotive force. That induced voltage is also known as electromotive force. That induced voltage is also known as electromotive force. I am not audible? Not clearly audible. Okay then. Okay, I will continue the class. So my voice is audible, but there is some noise, air noise is there, that's it, nothing else. So let me continue. Later I will take attendance. So whenever a number of magnetic lines of force or magnetic flux lines that are linking with the conductor or a coil change, then voltage is induced in the conductor, or if there are coils, then the voltage will be induced in the coil. Okay, so the change that is associated with the conductor, okay, change of flux, okay, the change of flux that is associated with the conductor can exist only when there is a relative motion between the conductor and the flux. Okay, so the relative motion can be obtained either by rotating the magnetic field or by rotating the conductor. Okay, simply in this diagram I am showing you that magnet is moving or the conductor is moving. What you can do is, instead of moving, you can rotate the conductor. There is another diagram here, see here. So you can see north pole and south pole of the magnet. Okay, and in between there is a conductor. So this is our conductor, this is our conductor. Okay, this red line is our conductor. So in between the north pole and south pole there is a conductor. So the flux lines, you can see the flux lines are traveling from north pole to south pole. So if suppose I am rotating this conductor, so I think I should, so you can see a conductor here, and you can I will just change the ink of this pen. So you can see these are the flux lines, magnetic flux lines which are traveling from north pole to south pole. Magnetic flux lines which are traveling from north pole to south pole. If suppose this conductor is rotated, okay, if this conductor is rotated, what will happen? The flux linking with the conductor will change. Okay, if the conductor is rotated, then the flux linking with the conductor will change. Therefore, voltage will be induced across the terminals of the conductor. Okay, so when flux linking with the conductor changes, then we can say that there is relative motion between the conductor and the magnetic flux that is induced between these two poles, north pole and south pole. So whenever there is a relative motion between the conductors, whenever there is relative motion between the conductor with respect to the magnetic field, then EMF will be induced. EMF means what? EMF means electromotive force. Okay, so if EMF is induced, then what will happen is, if there is a closed path formed by the conductor, if I close this, okay, so then current will flow through the conductor terminals. Okay, so in order to achieve the relative motion between the conductor and the magnetic field, what we can do is we can rotate the conductor. Okay, so you can see here in this diagram I am showing you here some n number of conductors. See, this is a conductor, so this is it. So it has n number of turns. So if a conductor has n number of turns, that conductor with turns, you can call it as a coil. Okay, if a conductor has n number of turns, then you can call it as a coil. So here you can see a coil here. You can see a coil with how many turns? 1, 2 and 3 turns. Just for example, I am showing this diagram. So you can see a coil with 3 turns here. So n number of turns, a coil can have n number of turns. So whenever this coil is rotated, okay, if it is either in clockwise or anti-clockwise direction, here you can see clockwise direction is shown in this image. So whether they are rotated in clockwise or anti-clockwise direction, there will be relative motion between the conductor and the magnetic field. Of course, here magnetic field will be stationary. Why? Because you are rotating the coil, so magnetic field will be stationary. Hence, one is stationary, other one is rotating. So there is a relative motion between these two, and hence voltage will be induced across the terminals of this coil. Okay. Now let us, as I have already discussed, the voltage that is induced, it will be directly proportional to the rate of change of flux linking with the coil. Okay, with respect to time, flux is varying. The flux linking with the coil is varying with respect to time. So the voltage that is induced will be directly proportional to the rate of change of flux linking with the coil. So this is our voltage. This is our voltage. E is proportional to d phi by dt. If you remove the proportionality, it can be replaced by a proportionality constant n. Just write it down. All of you write it down. Principle of Working principle of DC generator, the voltage, induced voltage. So the induced voltage will be proportional to d phi by dt, and if you remove the proportionality, it can be replaced by some proportionality constant n. So this proportionality constant is nothing but number of turns in the coil. So just now I have shown you this image. In this image you can see there are 3 turns, isn't it? This coil has 3 turns. There can be more than 3 turns. Some n number of turns can be there in the coil, which is placed in between these 2 poles, north pole and south pole. There can be n number of turns between the coils, n number of turns in the coil, which is placed in between these 2 poles. Okay, so the induced EMF will be equal to n into d phi by dt. So where n is the number of turns in the coil, phi is the flux. Okay, so that is traveling from north pole to south pole. Phi is the flux that is traveling from north pole to south pole. If d phi by dt is the rate of change of flux with respect to time. So the induced EMF. Okay, so I will erase the inks. All of you write down these equations. This is the voltage that is induced. Okay, this is the voltage that is induced in the coil of a DC generator. So what is the purpose of DC generator? So when some mechanical work is done, electrical energy is produced, isn't it? So when mechanical work is done means here what we are doing, here we are rotating the coil, isn't it? Here we are rotating the coil. When coil is rotated, what will happen? There is relative motion between this coil with respect to magnetic field between these 2 poles. Therefore therefore EMF is induced. So the induced EMF will be equal to number of turns in the coil into the rate of change of flux linking with the coil. Okay, so in order to understand this concept, so I am showing you this image. You can see a person, there is a hand here, there is a hand, you can see a hand here. Okay, a person is holding with the help of some support, he is trying to rotate the coil. This is our coil. Okay, this is our coil. So he is trying to rotate the coil. So when he rotates, its position changes. Okay, isn't it? So with the help of hand, actually manually it is never done. So the coil is never rotated with the hand. So how the coils are rotated, I will discuss. So in practice, coils are never rotated with the hand, but to understand the concept, just for namesake, I am showing you this image. So what happens here is, if the coil is rotated, here just for example I am showing you a hand. So with the hand, if you rotate, just for example, okay, so mechanical work is done. So when coil is rotated, we can say some mechanical work is done. So when coil is rotated, what is happening here? Voltage is induced, and because of the induced voltage, if the coils are forming a closed path, current flows through the coil. I amperes of current, you can see I here, I amperes of current flows through the coil. So because of mechanical work, that is input is the mechanical energy and output is what? Electrical energy. So generator function is what? It converts mechanical energy into electrical energy. Okay, so now let us see what is happening here. We are giving some mechanical energy, and what is happening when coil is rotated in the magnetic field, EMF is induced. So if you take your hand, right hand, this is our right hand, if you keep your thumb, forefinger and middle finger perpendicular to each other, okay, if you take your right hand, if you keep forefinger, middle finger and thumb perpendicular to each other, okay, then if thumb represents the direction in which the coil is rotated, okay, thumb represents what? Direction in which the coil is rotated, the motion of the coil, okay, the direction in which coil is rotated. If this forefinger, okay, this is our forefinger, so if the forefinger represents the direction in which magnetic field is flowing, the flux lines are traveling from north to south pole, isn't it? So if the forefinger represents the direction in which magnetic field is flowing, then the middle finger will represent the induced current, okay, or the induced EMF, or the direction of the induced voltage. Okay, so middle finger will represent the direction of the induced voltage. So this is the direction of the flux, forefinger gives the direction of the flux, and this is the external means mechanical force that is applied to rotate the coil. Okay, so if thumb represents the direction of the motion, the forefinger represents the magnetic field direction, then the middle finger will represent the direction in which EMF is induced. So this is known as Fleming's right hand rule. So you can see here in this image, okay, in this image if you see here, here you can see this is the direction of magnetic field, isn't it? This is the direction of magnetic field, and this is the direction of motion. Okay, means the conductor or the coil is moving in this direction, so perpendicular to that voltage is induced, okay, or EMF. EMF is nothing but electromotive force. The voltage that is induced in the generator, we call it as electromotive force. Okay, so this way will be perpendicular to each other. Okay, see one more image is there here. So this north pole and south pole, this is the motion of the conductor. If upper line represents the motion of the conductor, this is motion of the conductor, and if this is the direction of the magnetic field, then perpendicular to it voltage will be induced. Okay, so the direction in which EMF is induced in the conductor or the coil in the DC generator can be obtained by Fleming's right hand rule. Okay. Now there is a law which is known as Lenz's law. There is a law which is known as Lenz's law. According to Lenz's law, always the induced EMF, what is happening when coil rotates in the magnetic field? What is happening? Voltage is induced. When coil rotates in the magnetic field, voltage is induced. That voltage is equal to N into d phi by dt. So the induced voltage will always oppose the cause producing it. Okay, the induced voltage in the coil will always oppose the cause producing it. So since it is opposing the cause producing it, E will be equal to minus N d phi by dt. Okay, so what is E? E is equal to N into d phi by dt, but the induced voltage will always oppose the cause producing it. Therefore E will be equal to minus N d phi by dt. Now to understand it, you can see this diagram. You can see this is a magnet. Okay, sorry, this is a magnet. Okay, this is a magnet, cylindrical shape structure. What is shown here is a magnet. So from north pole what will happen? Flux lines will travel. Okay, from north pole, one second. Okay, from north pole flux lines are traveling. Okay, these are the flux lines. There is a conductor here. This is a conductor. Okay, conductor which is in the shape of a ring. Okay, there is a conductor here which is in the shape of a ring. Okay, so disturbance is there because of my laptop. There are fans inside my laptop which are making noise. Okay, so the disturbance is within the laptop actually, not because of the outside. I have even switched off the fan in my room. So I will change my device as soon as possible. I will change my device if I am about to take the online class later. So you can see here, this is a conductor which is in the shape of what? Ring. Okay, so this is my conductor which is in the shape of a ring, and this is my magnet. This is my magnet. This is magnet. This is the conductor. So the shape of the conductor is in the form of a ring. Now if there is a magnet, we all know that the flux lines, okay, magnetic flux lines will travel. Okay, so magnetic flux lines will travel from, from the north pole to south pole. So these are the flux lines which are traveling from north pole. Of course, we have not shown the direction that they travel north pole to south pole. If you want, you can draw like this. I have stopped it. Okay, from north pole to south pole they will travel. So you can see the flux lines. Now we already know when current flows through a conductor, magnetic field is induced. According to Fleming's right hand rule, you can even determine the direction of the magnetic field that has been induced. Okay, so when current flows through this, one second, I will change the ink color. So when since it's a so when flux lines are traveling from through this ring, okay, so through this ring, if there is rate of change of flux linking with this coil, then what will happen? EMF will be induced, and since it is forming a closed path, it is a ring means it is having a closed path, therefore current will flow through this conductor ring. Okay, so for the current to flow, for the voltage to induce in this ring, what should happen? Either the ring should move or this magnet should move. Okay, either the ring should move or the magnet should move. So the movement is not shown in this image. Either of them should move. So when voltage is induced in this ring because of rate of change of flux linking with the ring, what will happen? Current I will start to flow. So now when current is flowing, we know when a current carrying conductor is there, flux will be induced around the conductor. Okay, so that induced flux is this. This is the induced flux. This is the induced flux. If you carefully observe the direction of the flux lines, these flux lines, their direction is like this. What is the actual flux line coming from this magnet? Flux line, actual flux line direction is this. So what about this direction? You see the flux that is induced in this coil conductor is in this form, and the actual flux direction is in this form. Both are in opposition to each other. Okay, so both are in opposition to each other. So according to Lenz's law, whatever voltage that is induced, okay, whatever voltage that is induced in the coil, okay, that induced voltage will always oppose the cause producing it. Okay, that is E equal to minus N d phi by dt. Okay, there is another example, no need, I have explained it to you. Now, so I have been discussing DC generator, isn't it? Okay, so if we have a DC machine, it can operate as a DC generator as well as DC motor. How a DC machine can operate as a DC generator as well as DC motor? How is it possible? It is possible. Why? Because both DC generator and DC motor have similar construction. Construction is same. Okay, construction is same. Okay, since the construction is same, it can operate as DC generator as well as DC motor. Okay, their function is different. What is the function of generator? It converts mechanical energy to electrical energy. Motor converts electrical energy to mechanical energy. That is the function. Function is different, okay, but their construction is same device, okay, same device. See, if you have a mobile, you can use it as a camera, okay, you can use it as a video recorder, okay, you can use it as a camera to take the pictures, as well as you can call anybody using your mobile. It has multiple functions, okay. But we know camera is earlier days we used to have separate camera, we used to have separate video recorder and all, webcams and all, okay. So all those video cameras and all, everything was different. Now everything has come into one device, okay. So even though construction is same, function of generator and motor will be different. So same machine, you can use it as a generator as well as motor. So let us see the construction of a DC generator. This image is a bit clumsy, isn't it? This is construction of DC generator. So construction of DC generator or motor, I can say, the construction is same, okay. DC generator and motor construction is same. That's why I have written two titles here: construction of DC generator or DC motor. So 1 second. Of flux linking with the ring, what will happen? Current I will start to flow. So now when current is flowing, we know when a current carrying conductor is there, flux will be induced around the conductor, okay. So that induced flux is this is the induced flux, this is the induced flux. If you carefully observe the direction of the flux lines, these flux lines, their direction is like this. What is the actual flux line? Coming from this magnet, flux line, actual flux line direction is this. So what about this direction? You see the flux that is induced in this coil conductor is in this form, and the actual flux direction is in this form. Both are in opposition to each other, okay. So both are in opposition to each other. So according to Lenz's law, whatever voltage that is induced, okay, whatever voltage that is induced in the coil, okay, that induced voltage will always oppose the cause producing it. Okay, that is E equal to minus N d phi by dt. Okay, there is another example, no need, I have explained it to you. Now, so I have been discussing DC generator, isn't it? Okay, so if we have a DC machine, it can operate as a DC generator as well as DC motor. How a DC machine can operate? I will repeat. As a DC generator as well as DC motor. How is it possible? It is possible. Why? Because both DC generator and DC motor have similar construction. Construction is same. Okay. Construction is same. Okay, since the construction is same, it can operate as DC generator as well as DC motor. Okay, but their function is same. It can operate as DC generator as well as DC motor. Okay, but their function is different. What is the function of generator? It converts repeat the concept. So mechanical energy to DC generator, electrical energy. Motor converts electrical energy to mechanical energy. That is the function. Function is different. So here, but the construction is same. There is same device. You can see a person is holding same device. See, if you have a mobile, you can use it as a camera. Okay, you can use it as a video recorder. Okay, you can use it as a camera to take the pictures. As well as you can call anybody using around the conductor. It has multiple functions. So we know. Okay. But we know camera is there will be earlier days we used to have separate camera, we used to have separate video recorder and all, webcams and all. Okay, so all those video cameras and all, everything was different. Now everything has come into one device. Okay, so even though construction is same, so the function of generator and motor will be so same machine. You can use it as a generator as well as therefore. So let us see the construction of a DC conductor terminals. This conductor is a bit clumsy. In the magnetic field here, construction of magnet is moved. So construction of DC generator or motor. Conductor is moved. The construction conductor is moved in the magnetic field. DC generator and motor construction is same. That's why I have written two titles here: construction of DC generator or DC motor. The conductor is moved within the magnetic field. Again, there will be rate of change of flux linkage with respect to the conductor. Hence, voltage is induced across the conductor terminals. So, if the conductor forms a closed path, then what will happen is in the conductor current will be flowing. Okay. So, whenever number of flux lines, okay, linking with the conductor, or if we have more number of conductors which are interconnected to form a coil. Okay, so coil is formed by number of conductors. Okay, so see if this is a conductor, I can twist it, okay, to form a coil. So this is it. So if a conductor forms a coil, so the number of flux current I will start to change. So when current is flowing, voltage is induced. We know current when a current carrying conductor is there, flux will be induced voltage. You can call it as electromotive force. So that the induced voltage is also known as electromotive force. Now, induced flux is this. This is the induced flux. I will check again and again the induced flux. If you carefully observe the direction, I will not go to full screen. Why? Because I am unable to see whether class is going on or not. This is the induced flux. If you carefully observe the direction of the flux lines, these flux lines, they are the flux line coming from this magnet. Actually, flux line coming from this magnet. Flux line, actual flux line direction is this. So what about this direction? See, the flux that is induced in this coil conductor is in this form, and the opposition to so let me check. Each other. Okay, so both are in opposition to each other. So according to Lenz's law, whatever voltage that is induced, okay, whatever voltage that is induced in the coil, okay, that induced voltage that is induced, okay, that is induced, okay, that is induced in the coil, Okay, that induced voltage will always oppose the cause producing it. It's wastage of time, isn't it? Okay, that is E equal to minus n d phi by dt. Okay, there is another example, d phi by dt. Okay, there is another example, no need, I have explained it to you. Now, so I have been discussing DC generator, isn't it? Okay, so if we have a DC machine, it can operate as a DC generator as well as DC motor. How a DC